I'm Rebecca Lewington. Welcome to our podcast. I'm here with Micron high bandwidth memory expert Girish Cherussery. Now that's high bandwidth memory with capital letters, the fastest DRAM on the planet. I think it's a completely fascinating topic, both from a technology and business perspectives, and I hope you will too. So Girish, thanks so much for joining me.
Hey, thanks, Rebecca. Very excited to be here.
So first of all, tell us a bit about yourself. What's your background, and and what's your role at Micron?
Sure. Yeah. So I did my bachelor's in engineering in India, and like many other dreamers, wanted to come to the US and learn more about my electrical engineering and computer engineering background. So came here to do my master's. I went to Vegas to do it. There I had taken up some analog circuit design classes, which kind of perked my interest more towards the analog design. And that led me to Micron, where I joined in 2004 as a product engineer. And then I moved subsequently into DRAM design and worked in DRAM circuit design for about 12 plus years, moved into the business side of things. And I was very lucky to actually work on some of the cool products that we were looking at that point in time in terms of high performance memory space. And when you talk about high performance memory space, there's nothing faster and performing better than a HBM. And so started working on HBM as a product manager.
Right. So let's take a step back. What is high bandwidth memory with capital letters?
Yeah, no, it's a very fascinating question, because when I first took up the role in the business side, I was asking the exact same thing. Why high bandwidth memory? So based on what I have read and understood and what I believe is, as massive supercomputers came into being, they required a large compute. And so they inherently tended to go for CPUs and GPUs, and especially GPU with its massive parallel processing capability was a very attractive solution from a processing side. Now, once you have a fantastic processor with massive parallelism, you need something on the other side that feeds the beast. Especially when you think about the extensive amount of flops that you can pack on a reticle, meant that you also needed a memory that was capable of feeding the data needed for the processor to compute.
So what are flops and what's a reticle?
Flop is floating point operations. It's basically the number of operations, floating point operations you can do per second. It's big. And
so a measure of math, basically.
I'm sorry?
A measure of mathematical performance.
That's correct. That's correct. It's a measure of math. And depending on the level of precision you need, you have different levels of floating point operations. You can do a double precision, you can do a single precision, you can do a half precision. So that's a flop. And what's a reticle? So for anybody that is in the semiconductor manufacturing arena,
like us,
Micron, and we are the only memory and manufacturing company in North America and in the Western Hemisphere. So when you look at us, we talk in terms of die size and reticles. And reticle is basically, kind of think of it as a photograph, and the negative that you use to, I don't know, most of the folks that are listening to this podcast, probably the new generation, you've never seen a film and you've never looked at an analog picture. But back in the day, the analog photography used a film, and that's what they used to call the negative. And you use that negative to print the actual photograph. So think of your reticle as the negative for the printing of the design onto the wafer. And usually the reticle is a certain space, and you have certain number of dies that you print within the reticle before you move into the next reticle and try to print the next set of dies. And so when I say massive, pack on a reticle, in the past, the goal was always to shrink the die or keep the die size a constant, and you pack as many transistors as possible within that space. In the recent past, they've actually started growing the die to pack more transistors into the processor, but at an exponential scale now, because now you've actually gone in not only increasing the die size, but you're also packing in more transistors.
Right. Right. And to your point, there's not much point making a super, super fast processor on an enormous die that costs a lot of money if you can't keep it supplied with data.
That is correct. That is
so
absolutely.
You need a very fast connection between the memory and the and how do you make memory fast? I mean, you don't just do the same thing in memory. You have to do some other things.
Right. So HBM fits that spot in terms of trying to feed the beast. It has massive parallelism. So for the folks that have been listening into the recent GDDR announcements and stuff, that's one way of making the memory fast. You kind of toggle your data faster. The other way is to toggle your data fast, but also basically have more data lines that are more parallel that you feed the processor with. So that's one thing. And then the other thing is when you think about it, feeding all of this high bandwidth and stuff consumes a lot of energy. So you need to do this in a very energy efficient manner, because otherwise your power needed to send the data back and forth is going to become so massive that you're going to choke, because you have a limited amount of power budget at the system level. So you want to maximize it to do maximum processing, and you don't want to be wasting too much of energy moving the data, right? So you need to make this energy efficient. And when you talk about energy efficiency or power efficiency, then HBM is perfect for this, because it's what we call an in-packaged memory. Let me explain that a little bit. What it means is the memory sits right besides the ASIC or the SoC, GPU, CPU, whatever is the processing unit, it sits right next to it, which is very different from what it is on a traditional setup where there's a CPU on a motherboard and you have slots where you put your DIMMs with your memory, and then you have a channel which is on the motherboard that routes the signal back and forth. With the HBM, it's all in one package. It's a big, massive package with multiple HBMs in some cases on it. What it does is it limits the amount of energy wasted in moving data, because the data is sitting right close to the processing unit. So it's fantastic that way. But one thing that comes with this is now you've got a memory that sits really close to the processor, but that also means that you're sitting in the same package. So you're going to be limited by how much memory you can pack within that package, because your package size cannot be unlimited, right? Your technology doesn't scale beyond a certain point. So you want to...
Right. I mean, the biggest packages are about, what, 20, 30 millimeters on the side?
No, you're talking about 60 by 60 or 70 by 70 in this particular case in terms of millimeters.
But even then, you're packing in stuff that would have been this much circuit board with vertical DIMMs and all kinds of connections, and yes.
Yep. And so what is the one way for you to pack all that DRAM without actually compromising the space? One way to do it is, the easiest way to get more density is you put DRAM right next to each other. But the problem with that is now it's going to consume space. So what you do with this, you go vertical. You start scaling this on a vertical side, and you kind of stack DRAM on top of each other through what we call the TSVs, which are through silicon vias. Kind of think of them as you've got multiple layers of paper, and you've got a little toothpick or a pillar that goes between the different layers, and that's the pillar that communicates between the different layers. In this particular case, it's a paper.
Right, and the vertical connections within chips are traditionally known as vias, which is why, and
that is correct.
Through silicon, because you had to make them all the way through the silicon wafer.
Yeah, that is correct.
A lot further than you'd normally make a via.
That's right. That's right. So now what you've got is a highly energy efficient in-package, high-density memory that basically feeds the big beast that wants all this data, right? So, this is very important for certain applications. When you think about it in the market, there are these HPC applications, kind of think of them as medical field, used in medical fields like genome sequencing, drug testing, especially relevant in today's COVID environment, right? You want to basically be able to, find a drug by simulating through the different sequences and finding a cure really quick. It is also used for, kind of identifying disorders and then developing the precision treatments that are needed, basically through simulations. And so that's one. There have been other applications of HPC. Department of Energy, especially in the US, is looking at HPC supercomputers to basically look at how they can optimize fuel efficiency, apart from many other things, right? And so stuff like this, cool stuff, but something that your desktop cannot do, you need a massive supercomputer to do.
Right, because in that case, they're taking the volume and breaking it up into a series of little cubes, voxels, and doing an iterative calculation of the air pressure, the air temperature, the air speed within each of those, and then coming back to transfer information between each of the voxels, between each run, and it's a big machine.
Right. And then there are more applications: climate simulations, financial sector.
Those are traditional ones like weather, those kind of things. Now, I was a little bit involved with some of the work preparing for Exascale, the biggest supercomputers of tomorrow. And one of the interesting nuggets is the specification calls them to be about 20 times more power efficient than existing supercomputers. And I believe that HBM has a big part to play here, right?
Absolutely. I mean, kind of think about one. You mentioned exascale computers. In order to build an exascale, and what we mean by that is exaflops, basically, machine. Imagine the amount of memory bandwidth that you need. It's going to be in the petabytes per second. And if you are trying to build that petabytes per second bandwidth from your traditional memory, the energy efficiency and the amount of memory that you need in order to feed that beast is just going to be massive, right? It's HBM is fantastic in that space, because now you take all of that and you try to bring all of that down into this little stack of memory or DRAM, which then feeds the beast with just a few placements of it on a package. It's fantastically energy efficient. So it has completely transformed how we think about supercomputers and the growth. And I think HBM has kind of made that linear curve go more into the hockey stick, as we call it, in terms of
that's what we need. That's what we need.
Right.
So let's delve a little bit deeper into how HBM is made, because it sounds terribly simple to say I'm going to stack some chips up, but it's not that simple, is it? Because for one thing, silicon wafers are nearly a millimeter thick, and if you were to stack 16 of these things on top of each other, it would be half an inch high. You can't do that. Tell me something about the challenges of actually making these things.
Right. So there are multiple areas where things get really interesting with HBM from a processing standpoint. So if you take a silicon wafer, it's typically about 775 micron thick. It's basically the thickness of a silicon wafer. Now, once you start printing all your die, your circuits, and everything on this wafer, now let's say you have multiple DRAMs on this wafer, and what you have to do is, in order to stack the DRAM, you want to make sure that the overall final stacked DRAM is about the same height as the silicon thickness of the SoC that it's sitting with. So in this case, let's say 720 micron or 770 micron. And what you're trying to do is, if you can put 775 micron thick DRAM and match the other side. So what we do is we basically go in and start thinning down the wafer, right? We thin it down to a point where there's these true silicon vias get exposed, and you then basically are able to stack one DRAM on top of each other and still be within the silicon thickness for the overall product. Now, where this gets really interesting is you have roughly about 6,000, what we call micro bumps at the bottom. That's the amount of the signaling and the power and ground pins that we have on the bottom. It's unlike anything that you see on a soldered package. This is massively tiny micro bumps. And these micro bumps, when combined with the TSVs, basically help you communicate up and down that DRAM in a very energy efficient way. But what it does is also, as you process this wafer so thin, when you get to the point where the TSV is revealed, in some cases, if you look at an entire wafer and you start thinning it, the whole wafer kind of crumples into what we think of it like a Pringle chips that just curls up, right? So you have to do some interesting processing challenges to make sure that the whole wafer is still aligned and it's you're able to still stack another DRAM die on top of the first DRAM die that you picked out. So it's a very, very complex and advanced back-end processing, which is unlike any other DRAM that you've got, right? It poses its unique set of challenges in terms of how we think about it with these tiny micro bumps, which if you think about it, you can't put it into a tester and test it because you damage those micro bumps. So you need to come up with unique ways of testing the memory. You need to find unique ways of basically processing the memory itself. And not to mention, you're trying to align these, roughly about the same number of TSVs exactly on top of each other such that you can communicate up and down that stack. So
right, and if it's a piece of silicon this size with 6,000 bumps on the back, it's the square root of 6,000 means they're about 1/10 of a millimeter apart or something ridiculous.
Oh yeah,
barely even see them. So let me get this straight. You take a wafer, and then it has 1,000-something steps to make it, and then you chop them up, and then you stack them up, and then you sit them down, then you chop them up, then you stack them up, and you put them together in a package. It's absolutely astonishing feat of nanomanufacturing.
Absolutely.
We're not done, are we? We're not done at this point, because now you have to get together with your customer, with their chip, and find a way to make the package work. So tell me a bit about that.
Yeah, no, talk about, advanced technology, right? Cutting edge technology. This is exactly where this is interesting because, for Micron specifically, we've done some of this through our innovative, breaking the memory wall, as we call it, through a hybrid memory cube, which is the HMC. We had done this a few years back. We've taken all of that learning, applied it into the HBM product that we are developing as well. So when you think about this complex system, now that you've got a cube with 6,000 little bumps at the bottom and all of them fantastically integrated with each other, integrated with multiple DRAM layers, now you got to ship this to your customer. And when you ship it to your customer, you got to make sure that this cube doesn't accumulate dust particles, or you maintain the cleanliness of the cube, right? We are talking about small, tiny particles absolutely disrupting the package integration, because what you do is then you take this cube and you take your customer's SoC, and it gets shipped typically to an end vendor, OSAT vendor, who then puts them either on a silicon interposer, which is another piece of silicon, right? And they try to basically then integrate that on a substrate, and then the whole package is built. So, if you kind of think about this, now once you ship the cube out to the customer, right? The customer has to go integrate this with their SoC and in their environment, which in many cases is not the same as the way we have it controlled in Micron. And this is where this gets really, really interesting, is this is what I call the true heterogeneous integration, because you're now marrying a memory process wafer with a logic process on a completely different silicon at the bottom. Or in some cases, it's not silicon at all. They use an organic substrate, or they use a certain bridge silicon. There are some interesting technologies on the packaging side that people have developed. So it brings unique set of challenges, because once you're done integrating, when there is a fail, who do you attribute the fail to? Do you attribute the fail to the memory? Do you attribute, because the memory vendor shipped it a known good, what I call a HBM cube. You attribute it to the ASIC, which was manufactured at a certain foundry. Well, more than likely, the ASIC foundry had already tested that ASIC and it looked good.
You'd think.
Or do you blame the integration process where you were integrating on a silicon interposer?
Right.
So that is one of the unique challenges of HBM, because now you are so closely integrated with your customer on how you build the solution. And this is a critical piece, because you cannot separate the two out. This is not a standard memory. You're very closely integrated with your customer on this solution.
From specification to design to manufacturing to integration, and ultimately, I imagine, a somewhat connected go-to-market motion. This is a completely different level of customer integration than I guess we're used to.
Right. It's what people call 2.5D, or it's a very, very unique way of basically building out your system, where now the memory is part of the system integrated right into the solution space, right from the day you imagine your problem statement and you design your system. The memory is always in the picture. It's not an afterthought anymore.
Right. And it changes the customer-vendor relationship considerably too.
Yep, absolutely.
Well, this is amazing. So just to finish, Girish, tell me what's next for you personally. What's your next big thing?
Yeah, so there's always an insatiable need for, call it memory bandwidth and memory density, especially, the application space around supercomputing and machine learning are only taking off. We are barely at the cusp of a massive change where I believe that data is the new strategic advantage that customers will think about. And when you think about data, what do you do with the data becomes the question. And with massive machine learning algorithms coming out, trying to predict what's next step and trying to manage your end user application around, trying to think about what it would be prior to even the end user knowing it, is a fantastic avenue for solutions like high bandwidth memory to be applied and to help make that integration and those solutions come to reality in the marketplace. So, there are interesting technology challenges. When we talk about power, now kind of think about it. You have a beast that is very powerful, and he's very noisy, and he's very very hard-headed. Because what I mean by that is you've got a CPU or a GPU or an ASIC that is extremely power hungry, and they dissipate a lot of heat. And when you mix their performance and the noise that they generate on the signaling side, creates some unique set of challenges on how we think about memory solutions moving forward. And so there is a need for a seamless integration of our memory into these SoCs in this kind of an environment. And that basically puts us in a very unique place for us to think about, how do we solve those problems for our customers? How do we make sure that the world can realize where this data can be consumed, processed, and you can learn from it and train the next set of data that is coming in to automatically predict what the future is. So it's a very enterprising space, and very excited about working on next generation solutions to solve these very interesting problems.
Oh, that's excellent. I'm pleased to hear you have a few more things to keep you busy for the years to come. So Girish, thank you very much for your time. This has been quite fascinating, and I'm sure all our readers and viewers and listeners will also benefit enormously from it. Thank you.
Thank you so much, Rebecca.